Okay guys, so I talked earlier and then my video stopped recording, so I'm gonna explain here again. Okay, so I think we are up to here in the last video. So you see this force, let's say if there's as a gravitational force, then if this is given as g m1 m2 by r square, but then see the mass of these protons, right? We are talking about two protons, so they have the same mass, which means m1 times m2 is the same mass. So let's say some m, that would be e squared, right? V squared in the equation. So constant, replacing these value of g, gravitational constant 6.67 times 10 to the power minus 11 times 1.67 times 10 to the power minus 27 and whole square. This is a square because we have two mass, right? m1 and m2, and they are the same mass. And then dividing that by r square equation, we call this as equation 1. R value is not necessary, you'll see in a minute why. Now let's call electrostatic force as F, okay, for now. Maybe not for another day. If just for now, let's call it F, okay? To make distinction between this force F, the gravitational force, and this electrostatic force. So F equal to K Q1 Q2 divided by R squared, okay? Now this is from Coulomb's law. Now you see Q1 and Q2, they also have the same charge because we are talking about the proton, and proton has a charge E equal to 1.6 times 10 to the power minus 19 Coulomb. So if we put that in this equation, it becomes this, replacing the value of a Coulomb constant K, which is 9 times 10 to the power 9 times Q1 Q2, that's really 1.6 times 10 to the power minus 19 whole square, right? E square because two same mass. And then divided by r square. Let's call this as equation 2. Now to see whether we can neglect gravitational force or not, we want to look at the ratio, right? We want to compare these, compare the magnitude of these forces. So let's, if we, to do that, divide this equation 1. Equation 1 has to do with the gravitational force. Divide that by the equation 2, which has to do with the electrostatic force. When we divide these two, we get this value, okay? So r square, they get cancelled out, right? This divide by this. And then after doing some calculation, you see I got this value on the top, on the bottom. And then if you plug this in your calculator, it turns out if, here I just, so if dash by f is this one, and I'm just writing here this as f equal to some value times f dash. So if you take this f over here, and then do some rearrangement, you get this, okay? So the electrostatic force F equal to 1.2 times 10 to the power 36 times F dash, okay? This is the gravitational force. So what does this really tell, guys? Electrostatic force is almost 10 to the power 40, not 1, not 2, 10 raised to 40, 10 to the power 40 times is stronger than gravitational force. Whoa, this is a very stronger force. That doesn't sound right. I mean, if that is the case, then how come we haven't, seen anybody, like anyone's body ripped apart while they are walking because of electrostatic force, right? This force is stronger, 10 to the power 36 or 10, close to 10 to the power 40 times. That's very strong. Something must be happening, Or have you seen someone, there was, you were going on this highway and then there was, some, I don't know, some vehicle got, ripped apart because of electrostatic force. No, you haven't seen that, right? So, and then think about it, it's not just here. This law is applicable in whole cosmos, okay? So think about, oh goodness, we have such a big cosmos, right? Like whole universe. And this force is that is stronger, electrostatic force, that is stronger, and we didn't even talk, maybe you guys haven't even talked until today about it. Electrostatic force is much stronger than gravitational force. So what's going on? So So what happens in nature is actually the object, right? The materials we talk about, they have the either positive, some of the materials have positive charge or negative charge. So the material, they don't stay charged for longer time. What happens is, let's say maybe this board is like, maybe it has some charge Q, let's say maybe 15 microcoulomb or something, and I have some charge maybe like a 2 microcoulomb or something. If I get closer, what happens? So the interaction happens there, and then the object, it turns out to be makes itself in equilibrium, meaning it brings itself to neutral form. Okay, so because of this interaction, because of this charge distribution, so charge distribution, and then because these most material, they tend to stay in a neutral form because of combining and recombining of charges. That's why we don't hear the explosion due to electrostatic force or anything like that. Okay, but in nature, electrostatic force is a stronger force in comparison to gravitational force. Okay, gravitational force is much negligible, but you and I are more used to seeing around, right? Like when you push some books, we can really feel gravitational force, but then we don't feel electrostatic force, is because most of the time the materials are in neutral form. Okay, so that is interesting thing about electrostatics. Guys, so let's do another example here on Coulomb's law. So there are three charges here, Q1, Q2, Q3. Your job is to determine the net force on this Q1 due to the presence of this charge Q2 and Q3. Okay, so you are given here given Q1 equal to 3 microcoulomb. Okay, Q2, let's convert this into Coulomb, 3 into 10 to the power minus 6 Coulomb. Q2 equal to minus 1 microcoulomb. Let's convert this into Coulomb. Okay, 1 into 10 to the power minus 6 Coulomb. And Q3 equal to minus 1 microcoulomb. So Q2 and Q3, they are same basically. Okay, Q2, Q3 equal to, let's convert this into Coulomb, so minus 1 into 10 to the power minus 6 Coulomb. Okay, so these are the information we are given. The configuration is like this, so I'll also draw it here because I have to, in a few minutes I have to do it anyway. So it to you guys anyway, so I'm going to draw it over here. So Q1 is over here, let's say this is Q1, there is a Q2 over here, and then Q3 is over here. In the diagram it's not given, so let's say this distance is 4 centimeter. Okay, and let's say the distance of this Q3 is 5 centimeter. Okay, from this, and then this side here, oops, that is Q2, this is a 3 centimeter. Okay, so you see this is a right angle triangle, right? So how are we going to calculate the force on this Q1? So what we are asked is this: what is F net on charge 1? This is what we are asked. So try to work on this, see how far you get. I'm gonna write this Q2 so a little bit. Where are we? Q2 here. Okay. Alright guys, so try and see if you can get, how far you can get, okay? And then after some time we'll do it together. Alright guys, so did you try anything here? I'm gonna move this away. Alright, I'll also write this information here, and so I know what is there. 3 10 to the power minus 6 Coulomb, and just write here Q1 equal to, sorry, Q2 equal to Q3 equal to 1, negative 1, minus 1 times 10 to the power minus 6 Coulomb. Okay. Alright, so let's see. So to find the force on this charge Q1 due to the presence of more than one charge, we use something called superposition principle. Okay, so let's see this one here real quick, and then we will work on that. You may have encountered this also when you are doing, you know, problems in Newton's law, right? So basically, in superposition principle tells us that the force F net on, let's say, J means some charge J is given as, I'm not going to write this vector quantity here. Force net F is given as, or maybe write it vector F, right? As force F on, let's say, force due to charge, let's say 1 on J, okay, plus force due to charge 2 on J, meaning in this case J is R1, okay, so the dot dot dot, so and so. So basically what does it say is, how do we want to write? If we want to find the force on this charge Q1 is, we want to look at the force on this charge Q1 due to the Q2 alone at first, find that one, and then we will also look at the, I forgot the vector sign, force on Q1 due to Q3, and then sum those together and then find the vector sum of it to see what's the net force acting on charge Q1. Okay, so this is a superposition principle applicable for other problem as well. And then when you have a, you know, when you want to find the interaction of charges between more than one charge. Okay. Okay, so now, so for using superposition principle, our F net should be what? F net 1 is equal to F1, not F1, right? F net on 1. So our charge is this charge, this is where we are going to look at. So the force on 1 due to 2, we write this as 2, 1, okay? So this means force F21 means force F due to charge 2 on charge 1. Okay, so this is an important thing to remember here. And let's say that as a vector quantity F2 plus force due to third charge Q3 on charge 1. Okay, so see, remember force F due to charge 3 on charge 1. So the one we are looking at, this one comes here later on. Okay, so this is what, this is, let's say this is our equation 1. Just giving it a name. Now, before we get there, we need to know a few things here. So let's look at force F21. Now let's look at from diagram. This is a positive charge, this is a negative charge, right? So what kind of interaction we will have? What happens, you know, this charge, do you think it will try to attract to this? Yes, right, it's gonna have interaction. So if F21 is going to be like that, okay, so it's going to go that way direction. What about these two charges, Q1 and Q2? Q3 is also, Q3 and Q1, they also have opposite signs, so, but then this is further away, so we will have force that will also be attractive force. So this force will be F31, like that. So maybe I'll write it outside, so So the force F 31 would be like that, okay? Now, so let's look at F21. For F21, what do we get? F2, using Coulomb's law, right? F21 is equal to what? K Q2, right? This 2 means 2 here, and Q1, because this is 1 here, 1 divided by R square, okay? This one turns out to be what? K, not K, just let's write down the value. We have K9, right? The value of a Coulomb constant is 9 into 10 to the power 9. Q2, what is the value of Q2? Q2 is same as Q3, which is minus 1 into 10 to the power minus 6 times Q1. What's the magnitude of Q1? Charge is 3 into 10 to the power minus 6, right? Divide by R, that's the separation between charge Q1 and Q2, so which is 4 centimeters. So 4, convert that into meter, 10 to the power minus 2, and then whole square, okay? Alright guys, find what you get here. So please put this in your calculator. Okay, so what did you guys get there? Value. So it turned out to be close to 16.9, negative 16.9 Newton. So this negative sign tells us something here. F21. Let's put this in the box. We'll need this again in a few minutes. A negative sign here tells us that the force F21 is attractive force, okay? So whenever you find this negative sign in a final answer, that the sign tells us the force is attractive, okay? Meaning we had two different, two charges with opposing sign, right? That's why we get the negative sign here, alright? So now we need to do the same thing for so we need to do the same thing for this F31, okay? So let's look at F31. Looking at F31, it's a little bit more, we need to do a little more detail than just this, because this is, look at this, the force experience is just straight along this x-axis, right, or x direction. Now for this one, it's not just x direction, it will have a two different, right? This is kind of going that way. So we will have both like x direction and y direction basically, right? We need to resolve this vector into x component and y component, okay? So before we do that, let's make angle theta here, because we will need that angle theta as well. We need to find that theta, okay? So F31, so before we do that, let me write this equation here. F31 vector is given as what? Maybe not write like this. Let's write it along x-axis, okay? So if along F31 along x-axis is just what? F31, this is the vector, right? So if you guys already finished writing this down, I'm going to erase it here. So it's like this. So we have to draw this triangle here, right? This is theta, and then this is given 4 centimeter, this is given 5 centimeter. So what can we use here? This is like, can we find the cos theta here? Curly base 4 centimeter by hypotenuse 5 centimeter, we get that. And then from here we can find theta equal to cos inverse of 4/5, okay? So if you do that, what value do you get? So please plug this in on your calculator. 36.8 degree. This is what I found. Okay, so now this force F31 along x-axis is what? F31 cos of theta, right? Cos theta, this is along x-axis. F31y would be what? F31 sine theta, okay? Now you see we have these same force magnitude is same, these two guys are same. So we want to compute only once, and then theta you do have to do twice because this is cos, this is sine, okay? So now let's look at the force F31. F31 equal to what? K, Q3, right? 3. Q, this is 1, so Q1 divided by R squared, which is what? 9 into 10 to the power 9. I'm going to erase this part, okay? This part is not.